We live in, perhaps we're cursed by, interesting times. Now, climate change is transforming our world. Its effects are many and varied. They're often, and perhaps this will increasingly be the case, they're often unpredictable. According to climate scientists, we're entering uncharted territory. Now, air travel, studies have shown, is likely to become a slightly more hair-raising prospect. Here's a recent example. An Air Canada flight bound for Sydney. It encountered sudden, severe, terrifyingly unpredicted turbulence. Imagine the interior of that plane. The passengers hit the ceiling. The plane dropped suddenly. Dozens of people were injured in that incident. Now, that kind of thing, according to my guest, may well be on the way to the new normal. Paul Williams is Professor of Atmospheric Science at the Department of Meteorology at the University of Reading, and he joins us via Skype. Paul, welcome.
Thanks, Jonathan.
To define our terms to begin, turbulence, what is that? What causes it?
Yeah, that's a great question. I mean, one answer is it's the hardest problem in physics, turbulence has been called, and that's because it's nonlinear, it's chaotic, it's random. The equations in mathematical terms are very difficult to solve. But it's around us all of the time. It's in your bathtub, it's in your cup of coffee when you stir in the cream, and of course it's in the atmosphere, and normally we don't notice it, but when we try and fly through it, and those random narrow currents of air push the plane up and down randomly, we certainly notice it then, and for nervous flyers it can be a terrifying experience.
Now, this can be predictable in certain instances. Planes can be flying into circumstances in which turbulence is likely, but on the other hand, it can come as a complete surprise to a pilot. How does that happen? How is it possible that turbulence can sort of come out of nowhere?
Well, it's because there are different kinds of turbulence. If you're flying, obviously, through a storm or near a storm, there's likely to be turbulence, but at least you can see the storm and it's on the radar. The pilots can see it through the cockpit window, so it doesn't tend to come as a surprise. But there's another kind of turbulence called clear air turbulence that's got nothing to do with weather systems. It's just generated by instabilities in the jet stream, and it's completely invisible and not picked up by the radar, and that's why it can be hazardous, because the plane is flying above the weather systems, the seatbelt sign is typically turned off, and just suddenly the plane hits this turbulence, and no one had any idea that it was there.
So when the plane hits that sort of a pothole, when it suddenly arrives in an absence of a supportive environment, how dangerous is that potentially to the structure of that aircraft?
Well, aircraft are designed to withstand even the strongest turbulence, and there are very strict requirements on the engineering. I've seen examples where a plane has been flying through extreme clear air turbulence and one of the engines has broken off mid-flight because the turbulence was so strong. That's very rare. And although turbulence does injure people, that's relatively rare as well. So I'm always conscious that some of your listeners may be listening on the way to the airport, and I don't want to worry anyone. The chance of you encountering turbulence that's so strong that you'll be injured is tiny.
All right, so let's get to the climate change part of this equation. Now, you argue that climate change could increase turbulence. What's the relationship potentially between these two things?
Well, it's all about the jet stream, and we know that climate change is having an effect on the jet stream. It's not just warming at ground level, although that certainly is occurring, but the climate is changing right up there at 35,000 feet as well. And the temperature changes are such that the amount of shear in the jet stream is increasing. And shear is the effect where the wind speed increases with altitude. And it's exactly that wind shear that causes turbulence. And this is not just a future projection based on climate models. We've, in a paper, analysed observations of the atmosphere going back to the 1970s, which is when satellites first started observing the jet stream. And the amount of shear in the jet stream has already increased by 15%. So this is all consistent with a lot more clear air turbulence in future.
So we're talking here about the turbulence that will result from the increasing velocity of air at those altitudes, or is it more complicated than that?
It's a bit more complicated in the sense that it's this quantity that meteorologists call the shear. So it's possible in principle for the shear to increase without the wind speed increasing. This gets a bit complicated, but it's the shear that matters, not the speed for turbulence generation. So it's the rate at which the wind speed increases with altitude, the different layers of the atmosphere moving at different speeds relative to each other. That's what generates clear air turbulence, and that's the thing that climate change is tampering with.
And is it purely an increase in temperature that is causing that tampering?
Yes, it is. And it's all because the warming is not uniform. The different parts of the atmosphere are warming at different rates. If all of the atmosphere was warming at the same rate, then there'd be no direct impacts on the jet stream, but it's temperature differences that drive the jet stream. And we know from satellite observations that the tropical parts of the planet at 35,000 feet are warming more rapidly than the polar regions. And so the north-south temperature difference, which is what drives the wind shear in the jet stream, is increasing itself as part of climate change.
So what is this going to do to long-distance air travel?
Well, I think when a plane takes off in a few decades' time, there could be 2 or 3 times as much clear air turbulence in the atmosphere. And yes, how will the aviation sector respond to that? The obvious consequence is that flight routes will become less direct, and if the plane has to fly around the turbulence, then journeys could lengthen. Or we could do something to adapt. We could build planes that respond better to turbulence. More modern planes have more flexible wings, for example. So the 787 responds better than the 747. So quite what will happen. Many things are changing. It's not just the climate and the amount of turbulence in the atmosphere, but many things in the sector are changing on these decadal timescales. So quite what happens, we'll have to see.
Does flying lower, does that get you out of this problem, or does that put you into turbulence from other sources?
It doesn't really help. We've analysed different flight levels, and we see increases at all flight levels. So the details vary. The precise percentage increase might be a little bit different, but no, there's no great benefit from flying at a different altitude. And in fact, you'd get away from the tailwinds, which is the beneficial thing as well. So a tricky one.
And you mentioned the discrepancies between equatorial and polar regions. Other geographic eccentricities in this effect?
Yes, possibly. I mean, we've done a global analysis. We started out looking at transatlantic flights, which is the busiest oceanic flight route in the world. But more recently, we've looked globally in both hemispheres. So it's the jet stream regions, the mid-latitudes in both the northern and the southern hemisphere. So that's 30 to 60 degrees north and 30 to 60 degrees south. That's mainly where the main jet streams are. And we see increases of several 100% in the amount of clear air turbulence in the next few decades at all of those latitudes. So these are busy flight routes. Most flights are at those kind of latitudes, unfortunately. Several
100%. That's quite extraordinary, though I imagine it's off a reasonably low base?
Turbulence is rare. So we know from measurements by planes that about 3% of the atmosphere contains light turbulence, and this is not the kind that injures anybody, but it might stress nervous passengers. But the severe turbulence has the potential to injure. Only, we think 0.1% of the atmosphere contains turbulence that strong. So even if it were to double or treble in frequency, we'd still only be talking about 0.2 or 0.3% of the atmosphere. So it will still be rare. A doubling or a trebling sounds dramatic, but we're doubling or trebling a small baseline, so it will remain small. But nevertheless, a doubling or trebling is something noteworthy and something we might have to do something about.
I mentioned the experience at the beginning of that Air Canada flight approaching Sydney. Are we seeing more examples like that?
It's difficult to say. I think that the expectation is that we will, but it's a bit like when we're asked, there's been a heat wave and has climate change caused that heat wave? That's a very difficult question for a scientist to answer, because you'd have to show that the heat wave would not have happened if we hadn't changed the climate, and it's not clear how to do that. But what we can say, both for heat waves and for turbulence events, is that the science is telling us that these things will get more common and that we will see more in future. But this thing of attributing an event to climate change and saying this would not have happened without climate change is a very tricky scientific problem.
It's not just the turbulence that's an issue potentially around climate-related issues and air travel. Tell us about high-altitude icing.
Yes, icing is a serious hazard to aviation. It's not something we tend to hear very much about, but the formation of ice on the wings of the plane, for example, or inside the engine, can reduce the lift force that's keeping the plane up. And even tiny amounts of ice, just an ice particle, this ice the size of a grain of sand, one of those per centimetre squared on the wing is enough to significantly reduce the lift, so that is a major hazard for aviation. Quite how icing will respond to climate change is a very open question that hasn't really been touched by scientists yet. It's a tricky problem, and we're certainly working on it, but we have no concrete results. So we basically don't know how icing will respond to climate change.
At a more terrestrial level, we have a lot of airports that are vulnerable to sea level rises or to flooding.
Yes, I mean, LaGuardia Airport in New York certainly suffered from the remnants of Hurricane Sandy a few years ago. It was shut for a few days because of flooding, and that's partly the storm surge from the storm, but also being exacerbated by sea level rise. And there are other impacted airports too. I mean, for example, a 3 degrees Celsius rise in air temperature reduces the density of the air by about 1%, and that means that the lift force that's helping a plane to take off is also being reduced by 1%. So it's common in the hotter parts of the world to schedule long-haul departures away from the hotter part of the day, just because planes can struggle to take off in hot weather. And of course, the effects of climate change will exacerbate that as well.
Changi Airport in Singapore, one of the world's biggest, raising its passenger terminal. Hong Kong constructing a seawall. We're making adaptations.
Yes, we are, and that's great to see. As a scientist, we publish results and we figure out what's going on with the climate system, and it's always nice when these results don't just disappear into the ether and into a vacuum, but that they're acted on when we have confidence in those projections. And so, yes, it's good to see that some airlines and some airports are taking this seriously. I mean, we have to remember that the lifetime of a plane is decades. So the planes that are being designed today will still be flying in a few decades' time when these turbulence increases will happen. So it really is critical to build a turbulence increase into the design parameters of the aircraft that are being designed today.
And designers are heeding that warning?
Yes, they are. I'm in contact with Airbus, who are interested in tweaking their design parameters just to make sure that the planes of the 2050s can withstand the more turbulent environment that they'll be flying through.
Paul, thank you so much.
My pleasure. Thanks, Jonathan.
Paul D. Williams is Professor of Atmospheric Science and Department of Meteorology at the University of Reading.